This is lecture 7.3 for AP Environmental at St. Albans. Basically finishing up the air pollution and air quality unit, tidying up a few things that we need to finish before being done with the chapter. So the first one, and maybe the big one, is what's called acid deposition. Used to be known as acid rain, but it can also fall as frozen precipitation. It can be acid sleet or acid snow, even acid fog. And it contains high concentrations of acids, primarily because of secondary pollutants, reactions in the atmosphere that will cause the formation of sulfuric acid and nitric acids from sulfur oxides and nitrogen oxides. The sulfur oxides are coming from coal burning power plants. The NOx is probably coming from your tailpipe of your car. So the source is of course combustion of fossil fuels. Now, it's important to note how it develops. You know, you have your primary sources, your primary pollutants, which are SOx and NOx coming from factories or tailpipes, reactions in the atmosphere with water, and then it falls back to the ground surface in lakes or onto croplands, etc. And you can see how that would be a problem. How acidic is acid rain? Well, not very. If you look at the scale of normal rain, the pH is around 5.5 to 6.5, slightly acidic anyway. Acid rain, though, is going to drop that by at least a full pH unit. And remember, pH acts like the Richter scale for seismic activity, earthquakes. It is logarithmic. So a single increase in pH from, let's say, unit 4 to pH 5 is an increase by an order of 10 times the concentration of the acid ion. So acid rain would fall in the range of something like tomato juice, which could be pretty acidic for people's stomachs. And certainly aquatic organisms are very sensitive to changes in pH. Anybody who has had a fish tank knows that you have to control carefully the pH. So aquatic organisms are really sensitive. Now, what's important to note here is down here at the bottom, that the prevailing winds in the United States blow generally from the southwest to the northeast or from west to east. And so there's parts of the country that are much more impacted by acid rain than others. So the red dots on this map show locations of major coal burning power plants. And remember, here is our prevailing wind doing this left to right, or sort of like this, bottom left to upper right. So east to northeast winds. And you can see this concentration of coal burning power plants near some of the historic big coal deposits blows that up toward the northeast and reacts in the atmosphere, the sulfur dioxides do, to form acid rain. So New England, upstate New York, the Adirondacks in particular, and central Pennsylvania have been very hard hit by acid rain. And also globally, places that are downwind of big industrial centers, Poland and Germany, tend to be impacted by acid rain as well. And certainly you can see Southeast Asia as well. So what does it do? What's the big deal? Well, the most costly effect of acid rain is probably crop damage. pHs that are too low will damage the ability of a plant to photosynthesize, and plants will die. So you can have massive crop loss if there's a big acid rain event. But other things that are interesting that do occur are chemical erosion of some monuments, especially if they're limestone, which is calcium carbonate, and that will dissolve in an acid. So very often you'll see something that looks like this. Very old gravestones or old statuary on cathedrals are eroded over hundreds of years of the Industrial Revolution, and burning coal have led to so much acid deposition that these things are disappearing over time. That's why it's hard to read a lot of really old gravestones, is because of acid rain slowly dissolving away that statuary. Other stuff that can happen is this. Acids, as you know, react with metals, and so it can mobilize and leach metals that are toxic in soils. Aluminum in particular, so it can cause death of plants, again, crops, but also forests. This is an interesting picture right here, which shows upwind in the Smoky Mountains versus downwind. And this is a place where acid fog occurs, again, from coal burning power plants. So these plants on the left side are getting hit by the fog, whereas these plants on the right side are downwind of the peak of the mountain, almost like the rain shadow effect, and they are protected from foliage loss due to the acid rain. And I saw this in person in the Smoky Mountains on some hikes I've done in the past. Let me go back. Other things that it can cause, of course, respiratory disease. And if there's a really bad event, if there's some acid rain with a really low pH, let's say one of these extreme region, it can cause acid shock, which will lead to a fish kill and death of aquatic organisms. So big losses of biodiversity. This is just a quick diagram you guys can look at on your own time that just kind of shows some of the effects: leaching of soil nutrients, release of toxic metal ions, aluminum in particular, tree death. We saw a picture of that, etc. More pictures of acid rain. Okay, that's enough on acid rain. Let's move on to a couple other issues before we tidy up and finish the unit. Air pollution around the world, air quality is deteriorating rapidly in those countries that are developing economically. China is a great example of this when it was developing so rapidly in the late 1990s and early 2000s that everybody bought a new car. They were building coal-burning power plants like crazy, and the air quality really was affected in a terrible way. And this link right here, I'm going to escape from this, and I've put this on campus, but you can look at real-time air quality data from anywhere in the world if you like. So I'm going to zoom in on one. And when I say real-time, I mean today, right now. So if we zoom into one close to DC, let's see here. What's this one? Looks like Aurora Hills, Northern Virginia. How about this one in McLean? So here's the air quality data from McLean, Virginia, and they are monitoring particulate matter, it looks like. CO2 is being monitored, but we can see that this is from 5 minutes ago, and you can look at this anywhere on the planet. It's kind of fun to look at places that have really terrible air quality. Here again, we can zoom in on someplace in Mexico, which looks like it has some pretty terrible air quality right now, definitely in the hazardous zone. Look at the color here and notice it's the hazardous. What is this place? Let's find out. It is Aguascalientes, Mexico, whatever that is. Notice they're monitoring, looks like particulate matter, ozone, NOx, and SOx. And you can look at data, look at the bottom of that box at the past 12 months, when it's been bad, what time of year. Take a look at this data. Ozone seasonally is worst in July, August, September. That's as we expect. Anyway, let's move back to this. That's an interesting website to look at where air quality is bad globally. So how do we address this? Well, in the United States, we passed the Clean Air Act in 1963, and then in 1970, it was significantly revised to include those big 6 priority pollutants, things that are monitored for decreasing emissions. And it has absolutely led to cleaner air quality. This is a graph that shows some air quality data in millions of metric tons released per year. And you can see 1970 versus about 40 years later in 2008, everything has decreased by at least 40%. And that's a significant amount of material that's been released. Lead in particular has shown some radical decreases. Now, this is an interesting data set because it's an ice core, much like what is used to study climate change, carbon dioxide levels historically. And we've got ice cores that go back reliably to 800,000 years ago, good records of climate. But all we really care in this picture is something like particulate matter and lead in particular. So take a look. The Industrial Revolution, we start burning coal significantly in the late 1700s, and then in the mid 1800s is when the Industrial Revolution takes off, and lead climbs precipitously. Now remember, this is an Antarctic ice core. There is no industry in Antarctica. So this is being circulated and then precipitated globally because of atmospheric circulation. So again, this is very far away from any industrial source. So you can see it continues to climb, lots of lead over the years until we hit the mid-1960s, early 1970s. And there is a precipitous drop in lead accumulation because of the Clean Air Act. So it works. So how does it work? How do they get the stuff out of the air emissions? A couple of ways. Usually it's called scrubbers or scrubbing or baghouse filters. There's a couple different names for it. But most of the time what you see coming out of smokestack is not smoke at all. In fact, it's just steam. But before the Clean Air Act is when you had lots of particulates, lots of NOx and SOx being emitted into the atmosphere. There's basically two kinds of scrubbers. One is called an electrostatic precipitator, and that pulls particulates out. Let me get that pointer going again. There we go. That pulls particulates out. Most dust has a slight static charge, and so all they do is charge up the smokestack or a needle or some sort of electroconducting material, and the dust will stick to it, and then they'll turn off the charge and everything drops off into a collector or a filter. That's one way. Another thing is called a water scrubber, and it sounds like what it is. Essentially, you shower water down through gases as they go out the smokestack. And things like nitrogen or NOx and SOx are both polar molecules, remember your chemistry, and they get dissolved by water. So you still end up with a waste disposal problem in both of these things. You know, you've got a solid waste when you're collecting dust, or you've got a liquid water which has concentrated acids in it. So you still have a waste disposal problem, but at least it's not being emitted to the global atmosphere anymore. Okay, finally is indoor air pollution. It's actually a bigger concern than outdoor air pollution because we spend most of our time indoors. You know, we sleep 8 hours a day, and certainly under a COVID-19 shutdown, we're inside a lot of the time. So there are 4 big players in indoor air pollutants. Anybody who's a smoker or lives with one knows it's an issue, but there's other things that come up with regard to indoor air quality. Formaldehyde is a carcinogen. It's in everything. New flooring, paints, some kinds of materials that you would put up on your wall hangings and things like that. And particles, PM, is usually associated with smoke as well. If you have allergies like me, I'm allergic to dust, but there are all kinds of things that can affect your air quality indoors, including, viruses, cooking odors. If you have a pet, you probably have an air quality issue because they release a lot of hair and dander, which is like dry skin flakes, kind of gross. They can be highly concentrated indoors, and the reason is because of it's a closed system. Your air is circulated inside the house through a filter, hopefully, but there's not a lot of free-flowing air to clean out those materials. So you can see here's a list of the kind of things that show up in air quality. Asbestos is an interesting one, not found much anymore, but it used to be included in your piping and paneling insulation. And if it's ever broken up or removed, you have to get people with moon suits and respirators in there to take it out because it's so bad for your lungs. We can skip this. Most buildings are pretty well insulated. Let's talk a little bit about radon. Radon depends on the geology. It's a naturally occurring radioactive gas. It's a decay product of uranium, and it's found more often in some kinds of rock than others. So if you happen to be sitting on a bad kind of geology, you're more susceptible to radon exposure. It usually comes in through the basement because the basement is below ground, but it can definitely cause things like lung cancer. It is a radioactive gas. And if you have some sort of comorbidity, like a smoking habit, then it can be a big player in the formation of lung cancers. And it's interesting, this stat says it's the second leading cause of lung cancer behind smoking alone. So I looked up DC risk map, and I put this link on your MySTA homepage. So this shows a geologic map of the DC area. Only DC and Maryland, no Virginia information here. And you can see that the reds and the purples are the places where there's high radon potential. And what's interesting is that most of those seem to line up with the pink or the purple geology, whatever that is, whereas all the safe spots seem to be in this other part of town where the geology is not. I think this is more of the hard rock geology. That would be Great Falls right there, so that makes sense. So, take a look at where you're located on this map. Radon is an issue if you go to sell your home. If you have an older home, you may need to do some radon testing, which is cheap and easy to do. But it is a source of potential air quality issues. Okay, good enough for that. VOCs associated with like new flooring or paint, whatever it might be, is another source of air quality. There was a big scandal a few years back. I might be on the next slide. Now, here it is. In the early 2000s, because Florida got absolutely ravaged with 4 different hurricanes that in 2004, and they were so desperate for building materials that they imported some from China. Well, guess what? Those Chinese drywall imports contained formaldehyde and sulfur oxides, and they caused acid damage in people's lungs, and there was a ginormous recall to get rid of those materials. So all this added up together, all these different sources of potential indoor air quality can lead to a thing called sick building syndrome, which is an actual diagnosed illness. The symptoms, unfortunately, are very diffuse and hard to nail down to one particular cause, things like dizziness or headaches, shortness of breath, and that sort of thing. And they can be minimized relatively easily by changing your air circulation design or using low toxicity approved materials. I think that's about it. Oh yeah, you should know indoor air quality is a big deal in developing nations because most of those, a lot of those cultures cook indoors using wood or charcoal or even animal dung, dried animal dung like cows and sheep. It's mostly grass, so it can be burned, but that emits a lot of smoke and there's a lot of associated soot and carbon monoxide poisoning associated with indoor air pollution. So this is a pretty glaring stat that indoor fuel burning can cause as many as 1.6 million additional deaths per year. And we have a sort of a symptoms, or sorry, a illnesses list down here, which go along with everything we've heard before: pneumonia, bronchitis, asthma, lung cancer, etc. And I believe that is the end of it for today. So thanks very much for watching. I'll talk to you soon.